The continue button on the laptop in just a second. I appreciate it. Thank you. All right. Thanks, guys. All right. Remember, you guys are reading on those books while I work through this video, okay? All right. Good morning, 8th grade class, both in person and online students. Today, we're going to be working on page 27 and a few pages up, but starting on page 27 in our STAAR packet. So go ahead and you'll turn to page 27. All right, so we're going over chemical formulas today. This is something that we've covered at the beginning of the school year and right before our midpoint. But chemical formulas, ladies and gentlemen, thank you. Chemical formulas is how we can tell how many molecules, elements, and atoms we have in a particular compound, mixture, or chemical reaction, okay? So first, we have difference between elements, atoms, and molecules. Elements are found on the periodic table. Every element is found on the periodic table. It's represented by capital letters. That's either one uppercase letter or two letters, the first capitalized and the second lowercase. We know this, and we're given the periodic table on the STARS test, so we shouldn't have any issues with that. Next would be atoms. Atoms are represented by a subscript, okay? The subscript is going to be the tiny little number at the bottom. That subscript is located after the symbol. It's written as a small number, and it tells us how many atoms, particularly of that element, there are. If there's no subscript, it just means that there's one single atom there. They're not going to write the number 1. Since they wrote the letter, that kind of stands in for there being one of those elements, okay? And you can see that right here for carbon. There's nothing after carbon, which means there's technically just one, okay? All right, and those are for our atoms. Now, when we're talking about molecules, we have to talk about the coefficient. That's located at the beginning of the chemical formula. It's a large number. And in order to figure out how many atoms we have to multiply coefficients by our subscripts, all right? Or our coefficient by our number 1. When we do that, we can figure out how many of each atom there are in all of these molecules. Because this number 4 right here is telling us that there's 4 molecules of CO2. So if you're looking at just the carbon, you would have 1 carbon in a molecule of CO2, but since there's 4 molecules, you have 4 carbons. And since in CO2 there's 2 oxygens, in 1 molecule you only have 2, but in 4 molecules you're going to have 8, 4 times 2, okay? So this big number right here is called your coefficient. And that small number is your subscript. As you see, we have 4 molecules of CO2 here. We have 1 carbon atom, and we have 2 oxygen atoms. All right, looking at this chart at the very bottom, we can fill this in. Determine the molecules, elements, and atoms for the chemical formulas, all right? And they've done a couple for us. They've done glucose up here, C6H12O6. As you see, there's no number in front of the molecule, which means there's just 1. All right, 1 glucose molecule. There's 3 elements, carbon, hydrogen, and oxygen. So that's 3 different elements. And then if you add up all the atoms, 6 plus 12 plus 6, you get 24 total atoms. And you do the same for these. Since there's 2 molecules of H2O, you have 2 molecules here. Hydrogen and oxygen, that's 2 elements. And then since you have 1 oxygen, but 2 molecules, that's 2 oxygens total. And since you have 2 hydrogens and 2 molecules of this, you're going to have 4 hydrogens total. So 4 plus 2 equals 6 atoms. Same thing here, 3 times 2, then 3 times 3. Add those up for 15. Let's do this one right here. For NH3, we have 4 molecules of NH3. 2 different elements we're working with, hydrogen and helium, hydrogen and nitrogen. And then we're counted up our elements and we have 16. That's 4 nitrogen, right? And 12 hydrogen. Add those together, that's 16. What's up? Oh, tape? Yeah, I got you. Tape. All right, and then down here at the bottom, we have 2 molecules, 3 elements total. You add them all up, you also have 16 total atoms. That's how we break down our chemical formulas. The STAARS test is going to ask you to do this. It's going to ask you to break down formulas just like this. All right, that's page 27, chemical formulas. Moving on to page 28. Since we know our chemical formulas now, we can talk about chemical equations. All right, there's two parts of a chemical equation, what's on the left and what's on the right. What's on the left is known as our reactants. On the left-hand side, we have our reactants. This is what we have before a chemical reaction takes place. Therefore, our products are on the right side of the arrow. And it's what happens after. It's what you have after a chemical reaction takes place. Thank you. All right, we have a strategy we like to use, the RAP, because it says reactants, arrow, products. The arrow is the chemical reactions, R is on the left side for reactants, products are on the right side. Okay? Think of a product as when you're done testing things and designing things, you're left with a finished project. Where's your phone out? Thank you, sir. Put your phone up, please. In the middle of the video, man. Y'all done? Mm-hmm. Rethink number 7. The rest of it's good. All right. So balanced and unbalanced chemical equations, all right? So since we know how many atoms are in a particular equation, now we can figure out if there's the same amount of atoms on each side of the arrow. And if there's not, it's called unbalanced, doesn't exist. But if it does, it means that it's balanced, and this chemical reaction can actually exist. So what we're going to do is we're going to break down this first one. So we're going to look at just the reactant side, which is everything to the left of the arrow. So on the reactant side, we have 2 elements argon, as you see, 2. We have 2 atoms of hydrogen, as you see there. And then we have 1 atom of sulfur. Now on the product side, which is to the right side of the arrow, we do the same thing. We have 2 argon, 1 sulfur, and 2 hydrogen. All the numbers match, it means that it's balanced. All right? Now down here on the second problem, we look at our zinc, we have 1, hydrogen, we have 1, chlorine, we have 1 on the left-hand reactant side. On the product side, we have 1 zinc, 2 hydrogen, and 2 chlorine. That does not match. That makes it unbalanced. This does not exist. And we know that because of the law of conservation of mass. Please, everybody behave. The law of conservation of mass. This says that matter cannot be created or destroyed. Sounds familiar? It's just like the law of energy, right? Energy can't be created or destroyed. It's just transformed. Matter is just transformed, but you're still going to have the same amount of elements and the same elements on each side of the equation because we can't make elements or atoms out of thin air. All right, the mass on the reactant side must equal the mass on the product side. So if you start with 100 grams of something, you're going to end with that same amount, 100 grams. And you can see that here. Calcium oxide and CO2, all right, come together to form calcium, I guess, trioxide. But it still is just 100 grams of whatever the product was. Okay, That's balanced and unbalanced. The STAAR's test will give you an equation and it'll want to know whether or not it's balanced or not. Or it'll ask you how to balance it. What numbers are you missing? You got to be able to add up all the numbers on both sides. Kimberly, you reading? Are you reading? Turn around, man. Do your work. Takes one person to pick up a highlighter. Come on. Yeah, the squeaky chair is kind of annoying, guys. So if you're in a squeaky chair, either just switch chair or try to sit still, okay? Appreciate it. All right, moving on to page 29. Oh, you're good, man. You can work. I'll check in just a sec. Thank you, man. Thanks for bringing it up. All right, chemical reactions. Chemical reactions. Thank you, guys. Appreciate you guys working hard. All right, chemical reaction, unexpected change, all right? An unexpected change in temperature is our first sign of a chemical reaction. If it gets hot or cold, it means it's absorbing, all right, or releasing energy. That's a sign of a chemical change, a chemical reaction. The next will be an unexpected change in color. If you put red dye in water, it's going to turn into red water. That's expected. But if you put that red dye into water and it turned blue, that's unexpected. That might be a sign of a chemical change. Next would be the production of a gas. Go ahead and set it right there for me. Production of a gas. All right. If you see bubbling or fizzing, okay, that means that carbon dioxide is being released. A lot of the time, carbon dioxide or some type of gas is being released. Next would be a production of a precipitate. It's a hard word, but all it means is that two liquids come together and they form a solid, precipitate. And the last would be a change in smell. If it starts to get an odor, guys, remember, once you're done with your work, I ask you to do one thing: stay quiet so everybody else can, okay? So if you're standing over somebody, you might have a hard time reading. So please go back to your seats. You're not bugging anybody, are you? All right, thank you. Okay, yes, sir. Yeah. All right, so change in temperature, change in color, gas formation of precipitate, or change in smell. All these are signs of chemical changes. Now, the STAAR's test loves to relate chemical and physical changes to your body. You need to know the difference between the two. Remember, a physical change is when you have the same substance left over. Maybe you break something, you tear something, change the shape of it, but you still have that original substance. Take apple and applesauce, for example. If you take an apple and smash it to the ground, now you have applesauce. It still tastes like apples, still has the nutrients of apples, all right? But it just looks different now. In fact, if you really wanted to, and you had enough time and enough science, you could probably put that apple back together somehow. But no chemical change really takes place. But if you leave an apple out on the counter for a month at a time, it's going to rot, change color, and smell. That's a sign of a chemical change. Let's talk about physical and chemical changes in the body. One thing that happens, let's sit at my I'll check for a second. One thing that happens in the mouth that's physical is chewing. You're chewing, you're tearing, you're ripping apart food in your mouth. All right? Next, you swallow it and it goes down your esophagus. The act of swallowing is pulling that food down into your stomach, using gravity and muscles to do so. So swallowing. Your stomach sometimes can growl whenever it's hungry. It's not doing things, change anything. It's just turning itself. It's churning. It's trying to get that last little bit of food in your stomach, and it's going to try to digest it. Your large intestine is pushing food, nutrients through it, trying to grab as much as it can. The large intestine is pulling. Lower in your body, it starts pulling the stuff out of your body, quite literally, till it gets to your rectum. And your rectum has the ability to close. If it doesn't have that ability to close, you have issues. Sometimes when people get older, they need adult diapers or colostomy bags so that because their rectum doesn't work anymore. Yours has the ability to close. That's a physical change. Next, chemical changes in the body. In your mouth, you're chewing and you're biting and you're doing something like that, but your saliva is actually starting to break down food. Enzymes in the saliva will start to break down things like carbohydrates and protein. While your stomach uses stomach acid to further digest and break down that food into almost like a pasty substance. Your small intestine soaks up nutrients. It takes those nutrients and it gets it into your bloodstream. Your intestines does doing most of the work for your digestive system. That's where you're getting your nutrients from. And your large intestine, well, you know that a chemical reaction is taking place if it smells. And I know middle school and high school kids, y'all fart. That's a sign that your body is doing a chemical change. It smells. It doesn't smell like the pasta you ate for dinner. It smells like a fart because it's chemically changing in your body. Got it? Good. That was page 29, guys. 29. All right, page 30. Got the time, so I'm just moving through here. Page 30. So anybody in class that doesn't have page 30 filled out, this would be a good opportunity for you. Contrell, Brock, you guys have page 30 and 31 completed in your packet? Just double check, because you guys are absent a little bit. So, no, you've been good, but Brock, you've been absent a little bit. Just double check that for me. Make sure that you guys have these pages completed. Calculating density. Density is easy, guys. Density is just your mass divided by your volume. That's the equation. You're actually given this equation on the STARS test on the reference sheet. But we also have a handy little triangle that you can draw for density. Same triangle as always. And we know mass is divided by volume. So you got to put mass over volume. And that only leaves density. And remember, with these triangles, cover what you're looking for, and that gives you the equation. If you're looking for mass, density times volume. Looking for density, mass divided by volume. Looking for volume, mass divided by density. Make sure you put your number in the right spot. So first thing we need to do is read a triple beam balance. Real simple. You have 3 bars here. Those 3 bars are going to have a weight. Those weight will be set at the measurement, and you just have to add those numbers up. I'm going to set the books right there. I'll check it in a second. So the first one is at 100 grams. The second beam is at 40 grams, and the third beam is at 2 grams. That makes a total of 142 grams. Finding volume of a square object is real simple, or a rectangle object. That's why we use chairs, Kimberly. All right, all you have to do is length times width times height to find your volume. 2 times 2 times 4 is 16. And that centimeters cubed is our unit for volume. Ladies, gentlemen, I hear a lot of conversations, please. Okay. So density equals 142 grams divided by 16 centimeters cubed. Mass divided by volume. So our density for this object is 8.875. We can round that to 8.8. This is easy. This is a regularly shaped object. It's more complicated when you're trying to find an irregular shaped object. Then you have to use the displacement method, which is pretty simple, but you have to be able to think outside the box. If you have a graduated cylinder filled with 5 milliliters of water, and you drop an object into that graduated cylinder, the water rises to 10 milliliters of water. That means that that object, in this case the apple, took up 5 milliliters of space. Because 5 milliliters minus 10 milliliters equals the milliliters of your object, 5. All right, and you know that because it displaced 5 milliliters of water. Go over here and look at your triple beam balance. You'll get your grams at 72. 70 plus 0 plus 2. And then you do the math, 72 divided by 5. And you get 14.4. That's your density, grams over milliliters. Something you guys would have worked on in elementary school would be the density of water. You remember the lab experiment where you mix some different liquids together, maybe like corn syrup, Dawn dish soap, oil, water, maybe some type of drink. You mix all these things together and they separate. because they all have different densities. The density of water is 1. Please get off the table. Please. Thank you. All right, density of water is 1. Right? If your density is lower than 1, you're going to float, like vegetable oil, 0.92. If it's greater than water, like corn syrup, it's going to sink, like 1.37. You can see that here. Not a lot of questions on the STAAR are going to ask you about this, but it is important to know about your density, okay? It'll ask you about floating or sinking. That all has to do with your density. Page 31. Last page. We're talking about energy flow. Energy flow. So there's really 3 ways to show energy flow. First is with a food chain, second was a food web, and third is with an energy pyramid. So we're going to draw each so you can kind of see what they look like. First, food chain. Hey guys, please. I'll ask you to do one thing after you're done, not talk to people who are still working, and that's exactly what you're doing. Please stop. She's not done. She's working. So go move yourself back to a spot where you're not bugging her, please. Thank you, sir. You did so well, man. Don't ruin it. Only got 1 page left. We'll open up for some conversation in just a sec. All right, energy flow, guys. Talking about food chain. So food chains, it shows the path of energy from one organism to the next. It always begins with the sun, because sun is where all of our energy comes from. Then we have our producers that get energy from the sun, and then we can draw some consumers. The arrows show the direction of energy. I'll check this out. So it always starts with the sun. Your first arrow is going to go to some type of producer, all right? Some type of plant or an algae, something that takes in light and turns it into food through photosynthesis. Producers are then consumed by consumers. Insects, smaller animals. Those insects or smaller animals are then consumed themselves by other animals, okay? And then those animals are eventually consumed by larger animals. Okay? And it's a one-way street. Now, food webs are a little more complicated because you're going to have overlapping food chains all linked together. Now, it doesn't need to start with the sun necessarily. It can start with your producer, right? But the thing is, a lot of producers are eaten by multiple animals. So the arrows are going to go to multiple things. And those arrows are going to go to different animals, but multiple different animals. Because a butterfly can be eaten by a snake. Butterfly can also be eaten by the rodent. The worms can be eaten by the rodent. Okay. Maybe you have a spider up here that likes to eat the insects, and he can eat all of these insects. Okay. And then the snake can be eaten by a bird. Eaten by a bird. All right. The bird can also eat the rodent. The snake can also eat the rodent. And you see, it's very interconnected. It does a much better job at explaining the biodiversity, the ecological diversity in an area. And the last is an energy pyramid. And real simple, you'll find lots of examples in your book on these, but you just need to know that your producers go on the bottom. All right, and we call these primary producers. And then we have consumers. In the next two levels, the first are our primary, and then we have our secondary. And at the top of the pyramid, we're going to have our apex predators. Those are those predators that nothing else can top. And there's other layers in between those, but you'll find those in your book. You can copy one over. This is our energy flow. Food chains, food webs, and energy pyramids. Important things, the arrow shows you energy flow. Predators from one may be linked to other food chains. And energy pyramids show the amount of energy moving from one level to another. All right, very good.